Hello everyone. Today we will be presenting our machine learning project on topics of choroidal neovascularization, localization in OCT image. So let's move to the agenda overview. Here is some list of the agenda. Move to the introduction. What is the OCT image? OCT or optical coherent tomography. It is the non-invasive imaging test that the doctor uses light waves to take a cross-section of picture of your retina, which the doctor can use it to detect the disease that you may have. Then, what is the neovascularization? Neo from new and vascular from blood vessel. This is the growth of new blood vessel in unusual area that can occur to condition like diabetic or the age-related macular degeneration. Going to the NV characteristic first. The NV can happen mostly in three cases: below RPE layer, between RPE and IMM, and above the IMM. Thinking this way, the RPE, it is the bottommost layer of the OCT image, and the IMM is the topmost layer of the OCT image. So the case that we want to focus on is the below the RPE layer. On that case, it will host the disease called CNV, or choroidal neovascularization. It is the growth of blood vessel from the choroid layer, which is the layer below the RPE, so below RPE. Here is the example of CNV cases. The yellow one is the CNV area that we have drawn based on the consultant of the doctor. Going on the significant application, early detection, consistency, and faster and more accessible. Early detection, CNV will start as a small spot going larger. So if you can build an tools or model that can detect when it is small, it can early detect the disease. And consistency, the tools need to be low, minimize the agnostic, lower FPR, lower FNR, and faster and more accessible. Since it is tool, so it can reduce the doctor workload and help the doctor to identify the disease quickly. The challenges. First challenges is the generalizability. The model trained on one dataset may not perform well on others due to the quality of the image, disease propagation, or the acquisition method, which will affect a lot when training and prepare of the data. And second one, the availability of data. The OCT data is a lot, but the one contain the NV, the label NV location is not. We need to label it by ourselves, and we need to consult the doctor a lot. And the earlier picture, we can consist and make the model harder to train and label. Problem statement, to go short, it can lead to vision loss. Existing work, there exists a lot of work, but not on our domain. It is on the OCTA, which is different from OCT. And even it were to happen, it will happen only on the detection, not localization. Some literature review, detection using VGG. This is the old ML method, but it's outdated. So we want to build our own dataset. We get the dataset from the Kaggle. We get from the research paper from the NFS company. We have provided the citation below. The EDA, we have found that the category of the image is CNV, DMV, Dryset, and normal, total of 4 classes. And the amount listed below, CNV normal is almost the same. DMV, Dryset is differ a lot. So we want to do the CNV and normal since the class distribution is not much. Then the dimensions. We have average total of 662 times 500 from all of the pictures. So we need to resize it to 512 for consistency. Some picture may be elongated, some picture may be just square. So we need to find the sweet spot. And image type, it is mostly JPEG from OCT image from Heidelberg Engineering Tools. Getting the data, we need to label it first. Then we use tools called CVAT, if open source free. We have labeled a total of 2,231 data, split it into 80-10-10 format, test, train, validation. Here is the data preparation step, the labeling. So framework, we want to start with the input, noise removal, and image classification, yes or no. If yes, then we try to localize the area of the NV. Moving on to models. By deep learning, since the picture of OCT is high complexity and visual variability. Some are long, some are noisy, some are irregular CNV shape. The traditional ML wouldn't work, so we want to go down deep, so deep learning. And superior performance in imaging tasks. For the past 3 years, deep learning have proven to be a good choice of doing some of the research, since the model have high accuracy on medical imaging tasks, robust to noise and artifacts, and it can do fine-grained localization. And lastly, end-to-end learning capability, data, segment, label, and train. It can do this by allowing end-to-end training by using deep learning. So the first model that we want to use is UNet. UNet shape as U. It is the encoder-decoder model like a transformer or some sort, which have the addition of the skip connection. So firstly, the input image, you input the image on left. In case it is RGB, so channel is times by 3, then passing to the encoder. The encoder acting like a normal CNN, convolutional, ReLU, and going down by max pooling and have a 2x2 strike or strike equal to, so divide the dimension by 2. When it's going down, thinking this way, it is like a zooming in to get the important features, but it reduces the image size. Going down, we reduce the image size, getting the important feature. And going down to the bottom, it is called the bottleneck layer. It is the deepest layer. It contains the compressed information about the image, the most important one. But when it go up the decoder, it is upsample. When it is upsample, it thinks this way. It is some to rebuild the image from the compressed step from the bottleneck. But when you upsample up, you rebuild, sometimes you may experience a feature loss, because when you going down, the most important feature may not go through. So when you upsampling up, it may be lost. So that's come in the skip connection from the encoder. Since encoder you haven't lost yet, you just concatenate it with the upsampling one, like U6 and U7 and U8 and U9. You can see the skip connection from left to right. So this hence the shape of UNet. Then the output is the segmentation mask of an image where the pixel is shown on the picture on the right, the original, and the below is a segmentation mask. The second model that we have is attention unit, which uses soft attention. Soft attention doing the if the relevant part of CNV, we get a larger weight, and the less relevant part, we get lower weight. We have implemented the function based on the equation down below: ReLU, sigmoid, resampler, and phi function. And here is our model parameters, and here is a code you can scan to see the whole attention unit training coding.
So, after looking at attention unit, let's check out another popular segmentation model, DeepLab VT+. This model starts with less than 50 to extract features from the image. Then it passes them to something called ASPP, or Ultra Spatial Pyramid Pooling. That's the part you see here. ASPP helps the model look at the image from different zoom levels using dilate convolutions. That way, it can recognize both small and large features, which is really useful when you're trying to localize CNV. Now, let's dive into lesson 50 a bit. In the beginning, it captures basic patterns like edge and shapes. Then it gets deeper and learn more complex features. And it uses residual connection, so it doesn't forget the important stuff along the way. At the end, it combines everything using global pooling to help decide where the important regions are. It is a solid encoder for this kind of task. Here, the big picture of DeepLab VT+. We start with the image, run it to ResNet, then ASVP, then the coding part, and outcome with segmentation masks. It's a good setup, but we thought we could take it even further by hybrid architecture. So, here what we built: DeepLab V3 plus Ultra. It keeps the ResNet and ASPP paths from DeepLab paths, but we added two improvements. The first one is CBAM. It stands for Convolutional Block Attention Module. Basically, it tells the model what to focus and where to look. This means model doesn't waste time on background pixels. It put more weight on the important features like the CNV area. Next, we added a decoder head inspired by Mark R CNN. This part includes a couple of convolution layers to fine-tune the features, and then it upsample the result back to the original size. So instead of really low layers marks, we get much cleaner, more accurate predictions. This table here shows how the resolution changed throughout the model. We go from 512 down to 32. That's where the model really learned the features. And then we gradually bring it up back to the full resolution with final output. Now, this might surprise you. Even though DeepLab with Plus Ultra have more stuff, like attention and new decoder, it's actually faster than the Ultra as you see. It's just only 32 minutes. So yeah, it's not only better, it's also more efficient. And we will walk you through the result of our projects. We test all the models on 500 images, half with CNV and half without CNV. The first evaluation format is confusion-semantic. That's used for eval the classification performance. As you see, the best one is the DeepLab VT Plus and DeepLab VT Plus Ultra. It has a little bit earlier, like a 3 image from 500. And the most error is attention unit. As you see, it has the most error from in among of all model. And the next evaluation is the segmentation part. We use F1 score for each image. As you see, we use only the CNV image for segmentation part. Then we got the average of F1 score. You see that DeepLab VT Plus Ultra has a 80%, which is the most one. And this is some example of the result. You can see that DeepLab VT Plus is kind of like the best one, but in some case, as you see, we walk you through. You see that DeepLab VT Plus and VT Plus Ultra has the best one. You can see that. But when it meets some difficult image, the DeepLab VT Plus is really error, as you see. But DeepLab VT Plus Ultra has boundary in the correct precision. That means DeepLab VT Plus Ultra is better. Thank you so much for your attention.